Hi everyone. So now we are going to talk about the mutual inductance of solenoid, a long solenoid. Okay. So let's talk about that. Initially, you have to have a very good idea about the picture. Okay, the image which is given here. So this is first one, the black one, which is solenoid one, and the n1 number of turns, and the second one, the blue one, which has the same length. Okay, so look at this, L1 is equal to L2. Both of them have same length, which is equal to L. And this one is actually a solenoid 2, and the number of turns is equal to N2. Number of turns is not equal. L1 lengths are equal, but number of turns are not equal. Okay. And also you have to, and they are coaxial. They are coaxial. They are coaxial. The axis is same. Okay. And both the both the axes are same. Okay. So first one, look at this one, A1. A1 is the area of the bigger one. Okay, so this is what is A1, and A2 is the area of the smaller one. Alright. So then also one more thing you have to note down, that is N1, small n1 and small n2 are the turn densities. I have discussed this before. Turn densities. So what is turn density? Number of turns per length. So look at this, small n1 is equal to capital N1, number of turns divided by length. And I can also write it as capital N1 is equal to turn density N1 into L. And number of turns N2 is equal to turn density N2 into L. Alright. So then, now we are going to talk about the magnetic field associated with coil number 1 when I1 is a current passing through 1. Okay, so the magnetic field, how much is the magnetic field associated with? I haven't represented the magnetic field exactly. And one thing you have to particularly note, I'll give you the note here. One thing you have to particularly note, that the length of the solenoids, are very, very greater than their radii. Obviously, it is greater than radii, right? But here it's considerably greater than their radii. So we can say that lengths, okay, both the lengths, and we can say that like here in this particular case, this is very important point, the magnetic fields inside the solenoid will be uniform. So the magnetic fields inside the solenoids would be uniform. Okay, this one you have to keep in your mind. Okay, this is a point you have to note down. Then look at this, B1 is equal to the magnetic field associated with 1 when there is a current passing through I1. Okay, 1. That is I1. So B1 is equal to mu 0 N1 into I1. Then we know that what is the equation of flux? Flux is equal to B dot dA. Okay, integral B dot dA. And phi 21 is equal to integral. The integration should be along A2 because we are considering A2, right? Yeah, that is the if current passing through this one, a small one, I mean this one A2, and this second solenoid, then the magnetic field associated with will be this one A2. Even the current is passing through 1 or I1, then also the magnetic field will be associated with, because the area is less known. Yeah, so that is why phi 21 is equal to integral A2 B1 dA. Okay, what is this? Like integral B1 you can take outside, and the integral dA, that is A2. Okay, the total area A2. And since theta is equal to 0 degree. Okay, and again, because I told you the magnetic field will be uniform. So here it will be uniform. So the area and this one, both of them have in the same direction. So look at this. At this point, B is in this direction, and we know that area is also in the same direction. Okay. So again, so we can write phi 21 is equal to mu 0 N1 I1 A2. So why? Because mu 0 N1 I, that is what is B1 from this one. Okay. So then the total flux linked with the total flux linked with the second coil is equal to N2 into phi 21, which is equal to, what is N2? N2 is equal to N2 into L, small n2 into L mu 0 N1 I1 A2. So N2 into phi 21 is equal to mu 0 N1 N2 A2 L into I. Okay, and we know that we have the equation N2 into phi 21 is equal to M21 into I from the previous one, right? So M21 into I. So from that I can write M21 will be is when you compare these two equations. This is equation number 1 and equation number 2. When you compare both the equations, then we can write M21 is equal to mu 0 N1 N2 A2 L. So I can write M21 is equal to mu 0 N1 N2 A2 L. So this is what is the equation. This is what is the important equation of M21, that is mutual inductance of one solid, second solenoid with respect to first one. Mutual inductance of first solenoid with respect to second one is an assignment for you. Assignment. This is assignment number 2 that I am going to give you. Assignment number 2, that is mutual inductance of, you have to do it yourself. What you have to do? I think you got these steps, right, till here. So now you associate the second one with respect to first one. Okay, then you will get the same answer. M12 is equal to mu 0 N1 N2 A2 N. That is what is our aim. That's what our aim. So M12. So you have to keep in your mind, we have to get M21 and M12 as the same. So then work on it. Okay, the same steps you can continue from here to here. You can continue the same steps, then you will get it. Okay. So M12 is equal to mu 0 N1 N2 A2 L. So from that I can write it as both are same. So M12 is equal to M21, which is equal to, we can commonly call it as M. That is a mutual inductance of one coil with respect to another. So then M is equal to mu 0 N1 N2 A2 L. So this is like for what is this? Permeability of free space. So if the permeability is like, it's a common value, right? Yeah. So I can write mu into N1 N2 N1 N2 A2 L. Instead of mu 0 you can write mu. Okay. So also you can write this is mu 0 mu R N1 N2 A2 L. Okay, this is the equation of mutual inductance of a long solenoid. Okay, long solenoid. So you can keep in your mind this. Okay, so we will discuss more things about this. Okay, and we have to discuss some problems as well. Thank you.